Hello, everyone. Welcome to the QuantUniversity Fall School. Today, we are fortunate to have Dr. David Broniatowski from George Washington University. I hope pronounce your last name correctly.
That was great. Yeah,
David.
that was good.
So yeah, I have a really long last name, so I always try to see if I can pronounce all names correctly. So David and I got to know each other when I was referencing some of the NIST publications on explainable and interpretable AI. And a common friend of ours, Patrick Hall, made the introduction. So Patrick, as you all know, has also presented at the QuantUniversity Fall School before. And I requested David to present some of his work. And we had a really good chat about some of the research work he's been doing, some of the work he's been doing with NIST. And as you all know, with NIST engaging in new efforts on formalizing AI risk management, I thought the topic is very much contextual and relevant to today's discussion on how to adopt AI products responsibly and also in a trustworthy manner. As you all know, most of the audience we have in the QuantUniversity setting are people coming either from a data science or machine learning or in the quantitative finance world. And with a lot of data-driven decisions happening in our world, it becomes very much contextual to have a discussion on what does explainable AI mean? What does interpretable AI mean? And how do you kind of formulate that into the discussion? Brief introduction to David. Professor David Broniatowski conducts research in decision-making under research, group decision-making, system architecture, and behavioral epidemiology. This research program draws upon a wide range of techniques, including formal mathematical modeling, experimental design, automated text analysis and natural language processing, social and technical network analysis, and big data. Current projects include a text network analysis of transcripts from the US Food and Drug Administration's circulatory systems advisory panel meetings, a mathematical formalization of fuzzy trace theory, a leading theory of decision-making under uncertainty, decision-making under risk, derivation of metrics for flexibility and controllability for complex engineered social technical systems, and using Twitter data to conduct surveillance of influenza infection and the resulting social response. All fascinating topics, David, and I'm very fortunate that you're able to spend some time with us. Welcome to the QuantUniversity Fall School, and I will hand over the stage to you.
Thank you so much, and thank you very much for having me. My name is David Broniatowski. I'm here as a faculty member from the Department of Engineering Management and Systems Engineering at the George Washington University. I will start presenting my slides. Just throw those up real quick. This is work, or based on work, that I did while a NIST faculty fellow. Hopefully you can all see my screen here.
Yes, you can see it.
Wonderful. Okay, so the name of the presentation I'm going to give is Psychological Foundations of Explainability and Interpretability in Artificial Intelligence. And, because of the nature of the format here, I'm going to sort of give an overview of the paper itself. For those of you who may be interested in the paper and some of the details underlying the conclusions that I present here, I'll refer you to the URL at the bottom, which is posted on nist.gov. As I said before, this work was conducted as a NIST faculty fellow, and nothing that I say here is intended to represent the official position of the U.S. government or anything like that. I'm presenting this in my capacity as a GW faculty member, but I will provide an overview of the paper. So our agenda for today is as follows. I'm going to make a case that interpretability and explainability are actually distinct requirements for machine learning systems. And the reason why I'm making that case is because often the terms interpretability and explainability are used interchangeably. They're used to represent one another, whereas in fact, from the perspective of the psychology literature, they often mean quite different things. Specifically, an interpretation is the ability to contextualize a model's output such that you can relate it to its functional purpose and the goals, values, and preferences of end users. So for example, if you have a system that is designed to interpret a credit score, the interpretation, or to generate a credit score, the interpretation of that credit score may mean something for the user like, well, I don't think you're going to get that loan. You can't get the loan. You can't, as a consequence, for example, buy the house. That might be one interpretation. Whereas the explanation, in contrast, refers to the ability to describe the mechanism or the implementation, or the causal story that led to an algorithm's output. Often this is for the purpose of debugging. So for example, if the interpretation is that the credit score means you can't buy a house, the explanation might be, well, you don't have a long enough credit history, and the way that the algorithm operates is by looking at credit history. And so if you want to change your score, you would need to get more of a credit history. It's something that tells you how the result came to be. So another key insight here is that humans differ in systematic ways from one another. So, I was trained as an engineer for most of my career. And as engineers, we are often taught to think about the human factor as something unpredictable, something that really can't be captured in a reliable way, the way that we might with engineering metrics. On the other hand, in psychology, we think about humans as having systematic traits or systematic ways in which they differ from one another. And that's actually a perspective that I'm going to bring in here. Humans are, of course, variable, but they are variable from one another in systematic ways. And that variability is not infinite. And so because humans differ in systematic ways, we can actually use some of that knowledge to help us design our systems. There are people who prefer to make decisions based on detailed explanations versus those that prefer to rely on more precise interpretations. And what that means is that our interpretations and our explanations that our models are generating can be tailored to specific types of audiences and users. And so that's the sort of the conclusion I'm going to end with here is the system output should really be tailored to different user types if we truly want interpretable and explainable AI. So why does this matter? Well, there is a series of relevant laws and initiatives, and just a small number, small set of examples are presented here. For example, the Equal Credit Opportunity Act. I gave the example before of a credit score. Well, the ECOA, Equal Credit Opportunity Act, states that it reflects Congress's determination that creditors must explain the reason adverse action was taken. If somebody was given an adverse action, if their loan, for example, was denied, the Equal Credit Opportunity Act requires a creditor to explain the reason why that loan was denied. And if the loan was denied because of an algorithmic recommendation, of course, it's necessary to understand why the algorithm did what it did. A creditor must disclose the principal reasons for denying an application, etc. GDPR, European Union's General Data Protection Regulations, also states that human subjects about whom data are being collected have the right, quote, to obtain an explanation of the decision reached after such assessment and to challenge the decision. So if an algorithm is being used to gather data about someone, for example, perhaps a social media platform is gathering data or a search engine is gathering data, according to GDPR, a human subject can then go to the company that generated that algorithm or that is using that algorithm and request an explanation of how the data are being used. And if a decision is being made, they can challenge that decision. So of course, this imposes a regulatory requirement on the users of these algorithms that is explicitly related to explainability and interpretability. And within the United States, DARPA, the Defense Advanced Research Project Agency, has recently invested significant resources into what they call the XAI program, the Explainable Artificial Intelligence program, which is in large part about trying to figure out how to create algorithms for explainable AI. So there is no shortage of interest in this topic, and it has clear real-world consequences. Then the question becomes, what is the definition of interpretability? What is the definition of explainability? And so here are some examples that are out there. For example, Doshi Velez and Kim in their 2018 paper state that interpretability is, quote, the ability to explain or present output in understandable terms to a human. So they define interpretability as the ability to explain. Whereas Singh defines an explanation as a collection of visual or interactive artifacts that provide a user with sufficient description of a model's behavior to perform tasks like evaluation, trusting, predicting, or improving a model. So for Singh, an explanation is really primarily about debugging a model. It's giving people the reason why the model is doing what it's doing so you can make the model better. Per Gilpin, a good explanation occurs when you can no longer keep asking why. So explanations are about asking why and basically chasing down a chain of these questions. And for those of us who've raised toddlers, one might wonder whether it's possible to ever stop asking why, but it is something that Gilpin includes in the definition. Rudin, on the other hand, notes that interpretability is actually a feature of the model. It's something that makes the model constrained in form so that it's useful, or obeys knowledge of the domain, such as monotonicity or etc. And so an interpretable model then is one that is a constrained model, whereas according to Rudin, explainable model is different, one that is a second post-hoc model to explain the first one. So you might have a very complex model, such as a deep learning neural net, and an explainable model is simply a second model that tells you what the first model is doing. So these are all very different definitions of what is interpretability and explainability. And these people are all leading thinkers in the field. But one thing that they all have in common is that these definitions reference factors that are outside of the scope of traditional machine learning design. If you want to know, is a model understandable to a human? Well, you have to ask a human. If you want to know if somebody can no longer keep asking why, there has to be a person asking why. It's not the algorithm that asks why. And similar sorts of considerations apply to each of these definitions. And so that really motivates looking at the psychology, how humans interact with these models. And so the claim that I'm going to make here is that interpretability and explainability are psychological constructs. They're fundamentally constructs, they're fundamentally concepts that occur within a cognizing human mind. And furthermore, they're distinct from one another. So what do I mean by that? Well, it's important for us to start out by defining some terms, and these terms draw on a theory that is called fuzzy trace theory. Fuzzy trace theory is one of the leading theories of decision-making under risk. And as was stated before, NIST is increasingly moving in the direction of formalizing risk assessment for artificial intelligence. And so we think that this theory, which is about how people make decisions given risk, is especially relevant. And so verbatim here is essentially how risk information is represented in memory. So what I'm showing you in front of you on the slide is essentially verbatim information. This is information about the hourly forecast and the likelihood of rainfall. And so what you see over time, and moving from now through 12 a.m. on this would have been on December 16th, 2020, is the amount of rain that some model predicts you can expect to get. And so let's say, for the sake of argument, at 8 p.m., we notice that the amount of rain is 4.77 millimeters per hour, which they call heavy intensity rain, at 4.3 meters per second wind. All right. So a verbatim representation would simply be that. It would simply be 4.77 millimeters per hour with 4.3 meters per second wind. And now if I were to tell you to wait a week and then repeat those numbers to me, you would probably have trouble. You might remember heavy intensity rain. Heavy intensity rain is the meaning of those numbers. But if I were to ask you, well, was it 4.77 or 4.75 or 4.79? You might have some trouble remembering that. Verbatim memory is memory that is for these sorts of precise details, but is nevertheless brittle and easily forgotten. It's a detailed symbolic representation of our stimulus or the data. It's generally a memory for model output. In contrast, verbatim is compared to gist. Gist is a bottom line meaning. And initially, the concept of gist came from psycholinguistics, and it captures the idea of what does all of this stuff mean. So if I were to go back and say 4.77 meters per second, which of these two pictures, the sunny fun time at the beach or staying at home in the rain, is more likely to be the case? Well, if you're getting 4.77 meters per second of rain, you're going to stay home. You're not going to go to the beach. So the gist interpretation basically says, well, that means it's going to rain. That's the bottom line meaning. It's a meaningful bottom line representation of the stimulus. And, that, of course, is associated with certain other features stored in long-term memory, such as values. So for example, if you don't like getting rained on, if you don't like staying home, if you like going to the beach is good, staying home is bad. You might say, oh, 4.77 meters per second of rain. Oh yes, that's bad. I better make plans for something else. So again, to contrast gist and verbatim, gist is a simplified bottom line meaning that captures the meaning of the stimulus, or if you will, the interpretation of the stimulus. Whereas the verbatim is the stimulus itself, or a detailed representation of the stimulus itself. It's what you encode before making meaning when you see model output. So why is this distinction important? Well, we contrast gist and verbatim, which is about what you see and how you interpret it, with an explanation, or the result, how a result came to be. So nothing that I said before explained how the model decided that 4.77 meters per second was the right answer. Now, if you are a meteorologist, you might have something that looks sort of like this, where you have advancing cold air behind a cold front, and you have receding warm air ahead of the cold front, and then you would be able to construct a detailed fluid dynamics model regarding the likelihood of rain. And that detailed model would suggest an explanation. It would say, well, the reason why we expect 4.77 meters per second of rain at 8 p.m. on a Sunday, for the sake of argument, is because there is an advancing cold front, and advancing cold fronts create a pressure differential, etc. That would be the explanation. And if we wanted to have an explainable output for our algorithm, we would want to be able to have the output give us something kind of like that. So how do we bring this all together? Well, machine learning generally takes a family of models over here, takes training data as input, and fits that family of models to the training data to generate a single fit model. That fit model is then evaluated against some holdout data or test data in order to make some kind of prediction. In this particular case, probability of rain. That prediction then gets shown to a human that encodes it into a verbatim representation and a gist representation. The gist, of course, is ultimately the interpretation. The verbatim is the model output. And then if we see what the model is doing under the hood and we can make sense of that, that might give us the explanation. And these things together all sort of feature in to make a decision. So for example, some people, there are individual differences. Some people are more risk-taking than others. Some people are like, you know what, I'll just take an umbrella and I'll go to the beach. And if I get rained down, I'll go home, no big deal, right? Other people will be like, you know what, no, I'm going to stay at home. I don't even want to take the chance. And those are individual differences that may drive individual humans' decisions. So that's sort of the framework that we're going to take to discuss what we're seeing here. So to sort of drive this point home, I want to give you an example in the context of antibiotic prescription using a very simple model, a regression-based model. So what we have over here is the output of a commonly used model, the Centaur scale, for making a decision about whether or not someone should be treated for strep throat. And what you see here in this box on the left is what the actual model formulation looks like. It's simply a logistic regression. And the model itself has the following coefficients and the following features: number of exudate or swelling on tonsils, the presence or absence of swollen lymph nodes, whether or not someone has a cough, and whether or not someone has a fever. So you can go online and you can find a Centaur scale calculator, and you can sort of put in different values for these different things, and what the model will give you is an output, which is your likelihood of strep. It's a number. And so in a sample of patients from an emergency room in 1981, one of the things that this paper found was that these were the features that were associated with a higher likelihood of strep throat. And so if we wanted to explain what's the model doing, well, one might say something like, when the model multiplies the coefficients by the variables and then sums the result, the probability that the illness is bacterial, or specifically strep, is between 5 and 10%, which indicates, yeah, you know what, that probably doesn't require antibiotics. So what is the model doing? How might we explain the model? Well, we would give them some explanation like this, and then we would perhaps try to translate that into a verbal description. On the other hand, if we wanted to interpret the model's output, we would need to incorporate a lot of background knowledge about the person doing the interpretation. So there are certain relevant values. Most people think that getting better is good and staying sick is bad. If somebody is using this model, it's probably because they're sick and they want to know, should I ask for antibiotics? Or alternatively, they're a doctor and they want to know, should I prescribe antibiotics? And so the doctor will have to take into account a lot of other features, right? Including what's the likelihood of side effects? You know, side effects are bad, no side effects are good. Unnecessary prescription can promote antibiotic resistance, which could harm others. Harming others is bad. Not prescribing won't harm others, that's good. So given these values, looking at the output of the model, one might determine, you know, the likelihood that antibiotics would help is basically nil. You see what I did here? When I say basically nil, I'm not using a reference to a number. 5 to 10% for some people may be essentially nil, and for some people may be meaningful. But actually the doctor making the decision about whether or not to prescribe antibiotics would look at that 5 to 10% number and would make a judgment call. That, you know, this is basically nil. This is, you know, not really likely. They might also take into account that the antibiotics could lead to uncomfortable side effects, and then using antibiotics when they're not necessary could harm others. And therefore they might come to the conclusion, you know what, this person probably doesn't have a bacterial illness. The risk of side effects is greater than the risk of getting better. And so they might just say, you know, no further testing is required. And again, this is a judgment call based on the physician's interpretation of what they're seeing from the patient and from the model. Now, physicians might also ignore the model. They might look at the patient. The patient may seem to be really sick. They may say, you know what, I think this model left something out. And so then they might prescribe anyway. Or they might say, you know what, 5%, that's not really essentially nil. Like this patient, there is a small probability that this patient could get some really, really bad complication. So you know what, I'm just going to give them antibiotics because it's better to be safe than sorry. Again, that's not a quantitative decision. That is a gist. It's a simple qualitative decision that draws on that particular physician's expertise. Okay. So what's another example of what a gist interpretation might be? I'll ask you to consider 4 machine learning classifiers, and I'll ask you which of these are the best. So let's say we have a naive Bayes model, and has this accuracy 26.7% and following precision recall, F-score, etc. Somebody looking at this data might say, well, you know what, the logistic regression seems to be the best because, for example, it's got the highest accuracy. But is that really true? Well, if we were to look at the categorical gist, and how do we make sense of these results? Well, let's take a look at the k-nearest neighbor, right? K-nearest neighbor has an accuracy of 52.4%. So let's say we have a binary classification problem, 52.4%. That's basically like a random coin flip, and assume the classes are balanced. So somebody with a little bit of expertise in machine learning would look at this k-nearest neighbor and they say, you know what, this accuracy is essentially nil. The others are accurate, or kind of accurate. This one is essentially nil. So they might say, well, you know what, let's just not use the k-nearest neighbor. It's not doing well. It's got basically no accuracy. But what's going on here? The naive Bayes, this is weird. It seems to have an accuracy that's less than 50%. So what's the gist of that? Is that this is a really bad classifier? Well, if the accuracy is 26.7% and it's a binary classifier, you could flip the labels. And if you flip the labels, then your accuracy looks more like 75%. And that's actually better than all the others. So again, somebody can bring their background knowledge to bear, and they would say, you know, this has got, in a way, a higher accuracy than these two, even though the number itself is lower, but you need the background knowledge to know that. Well, okay, so finally, what model do we choose? Well, one way that we typically choose models in machine learning is by using an F-score. F-score is a harmonic mean. It's a combination of precision and recall. And so, for example, we might combine the precision and recall and say, well, the support vector machine, that one has the highest F-score. So maybe we should use that one. Okay, but is this really the best model? I would take a look at this model and I would see it's got a precision of 1.0. That's 100%. And I'd say, you know what? That's kind of too good to be true. Maybe there's some kind of problem in the way that the model was implemented. Maybe the model has class imbalance problems. And I would say, you know what? The gist of this is it's too good to be true, and I wouldn't use this model. So very quickly, having gone through these four models, what I'm trying to communicate here is that oftentimes the gist goes beyond the numbers and draws upon the expertise of the person looking at the results to help make a decision about which models are better. This naive Bayes, on the face of it, seems to be worse than the others because its accuracy is below 50%. But you can get a higher accuracy, or actually the correct accuracy, by simply flipping the class labels. The support vector machine seems to be the best model, but it's too good to be true. The k-nearest neighbor seems like it's not accurate at all. It's got nil accuracy. And then the logistic regression seems to be the only one here that's actually got meaningful results. So having gone over what is an interpretation, a gist, now we ask, well, what is an explanation? What I'm showing you here is some prior work on mental models, and this is work by Moray from 1990, where he looked at how engineers think about the ways in which causality flows through very complex systems. In this particular case, he was looking at power plants. And he was saying, well, you know, you turn the switch brings current to a pump, that causes the pump to rotate, which increases the fluid pressure, and that creates a flow. We flip the switch, that also puts current to the valve, which increases the magnetic flux, which changes the valve stem, and that also increases the flow. This is a more detailed explanation, but of course there are levels of explanation. On a very simple level, you flip the switch, that causes the pump to rotate and the valve stem to turn on, and that increases the flow. And both of these are correct explanations. Only this explanation is more detailed because it's less abstract. So the key point here is that these are actually mental models, and they are also encoded in multiple levels of mental representation, and they tend to represent perceived cause and effect dynamics of a phenomena. So when we talk about explanations, generally we refer back to this mental model literature, and that helps us to figure out, well, what exactly is this model doing? Here's an example in machine learning of multiple levels of causal mental representation. This is a classic example from the sklearn, scikit-learn documentation, where on one hand, you may have the code, the Python code that implements a support vector machine. Okay, but that Python code is actually a detailed implementation of a higher level of abstraction, a mathematical formulation of a classification problem. And that mathematical formulation then has a representation, in this particular case, a visual representation as implemented in data. So I might ask you, well, which of these are a correct explanation of what's going on? And the fact is they all are, just they're tailored to different types of explanations and different types of audiences. For somebody who simply wants to know, why is it, for example, that this point was classified as blue and not classified as orange? Well, because it fell on that side of the line rather than on that side of the line. That's one simple explanation. But then they might say, but why did it fall on this side of the line versus the other? Well, for that, you'd have to get into the math. I'll say, well, why is the math the way it is? Well, because we encoded it using the following algorithms. And so this question of constantly asking why has to acknowledge the fact that what you're doing is you're going through different levels of abstraction and different levels of causal mental representation. And so finally, I want to talk a little bit about individual differences. Why do individual differences matter? Because going back to our representation over here, there's some people would say, oh, it fell on this side of the line. That's a good explanation. I'm happy with that. And then there are others say, no, 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 show me the data, show me the math. And they would really require a lot more detail. And that is a systematic individual difference that we can measure. So people differ in at least two relevant ways according to basic psychology. People differ from one another in terms of their personality traits. So for example, there's a personality trait called need for cognition that was developed by Cacioppo et al. That indexes how much people enjoy thinking. And people differ from one another along this personality trait. Some people truly enjoy thinking hard about what comes their way. And those people, what we found in some of our prior work, those people will tend to notice conflicts and differences, things that are weird in the data. They'll pay attention to the outliers. Whereas people who are lower in need for cognition may be satisfied with the first answer that comes to mind. On the other hand, people also differ in their skills. So for example, numeracy. Numeracy is mathematical literacy. Not everybody has the ability to make sense of a neural net, let alone a regression. They simply don't know what it means. And so that's another systematic difference. Both of these can be measured. And so variations between users in both traits, which is to say fundamental features of their personality makeup, and skills, which is to say things that they have been trained in or educated in, can lead to differences in how people perceive the output of machine learning models. If you give a very detailed mathematical output that looks like a regression equation, for example, if somebody doesn't have any numeracy, they're just not going to know what to make of that. That's for them not an explanation. And so we need to sort of take these into account. What you're seeing over here, and I apologize, this looks like there's a copy paste error of the image, but people also tend to rely on gist more so than in verbatim mental representations when making decisions. So not only do people differ from one another in terms of their personality traits, but according to fuzzy trace theory, and has been demonstrated time and time again in empirical studies, people differ from one another developmentally as well. And the more expert you become, notice again that experts are sort of at the developmental apex. These are people who are the best at a task, right? People who are experts paradoxically tend to rely more on gist and less on precise verbatim when compared to novices. And you can think about this in the context of a student who is just learning how to implement a model. Perhaps they've just finished implementing their model and they're looking at the output and they say, you know what? This model has an accuracy of 73.2%. And then here's another model that looks like it has an accuracy of 73.3%. You know, the student would say, well, you know, I don't really know, maybe they don't really know what accuracy means. They're just sort of learning these metrics. And they say, well, but that one's higher. That one must be a better model. Whereas the expert would say, you know, they're basically the same, right? The gist is that they're essentially the same. And so again, this takes us back to the example we had before, where the novice would look at this accuracy and say, you know what? 26.7%, that's terrible for a binary classifier. That's less than 50%. A coin flip is better than this. Yeah, I'm not gonna use the naive Bayes model. And they're gonna look at the support vector machine and say, wow, precision of 100%, that's great. I'm gonna use that one. Whereas the expert would draw the opposite conclusions. The expert would look at the naive Bayes and they'd say, no, 26.7%, that's actually what, 73.3%. You just got the class labels wrong. And that's slightly better than many of these models. And the support vector machine, yeah, precision's 100%, but you've got a problem here. This is too good to be true, and they would not rely on that model. So again, experts tend to notice these problems and rely on the gist. So how do these psychological approaches compare to algorithmic approaches? Well, what you're seeing over here is an example of the local feature importance paradigm. So a paper by Lime from using the Lime algorithm from 2016. And what you're seeing here is an example of a Lime output where you have a text as input, and the text is supposed to present the output of a classifier designed to tell the difference between whether the text reflects atheism or Christianity. This is one of the classic examples for Lime. And what do we see? We see, well, there are scores associated with each of the features. For example, EDU increases the likelihood of atheism, it appears, by 4%. And what's it picking up on? It's picking up on the fact that the text is coming from an educational institution. So I might ask you, does EDU actually indicate that the person sending this is atheist? Or might that be a case of overfitting? This has been used as a classic example precisely because there is some structure out there in the world that would seem to indicate that in general, atheist people may be more likely associated with academic institutions. But that's arguably a bias. That's not something that's baked into how the model is supposed to work. That doesn't say the text is itself about atheism. It's picking up on a spurious correlation. Similarly, this is what we see when we have lime applied to a husky versus wolf classifier. So this is a picture of a husky that was incorrectly classified as a wolf. And if you look at the explanation from lime, what you see it's doing is picking up on all the pixels that represent snow. And again, I might ask the question, well, are wolves really less likely to be in snow than huskies? I'm sorry, more likely than huskies. And again, this seems to be like a spurious correlation. And if you were to ask me, well, why is it that the model got this result versus that result? I would say, well, these local feature importance features help me to understand what the model is picking up on, but not necessarily why it did what it did. There's a similar approach, of course, when we use another leading model called SHAP, which relies on Shapley values. And again, what this will do is it'll give you the model output, and then it'll tell you for variations around the model output, if you were to change the different variables, what would this mean for the actual model's prediction? And so I would argue here that these may not be explanations in the same sense as the psychology literature implies. Recall that explanations tend to be causal, and what a lot of these explainable algorithms are doing is they're presenting a localized correlation. Are we, and I might ask the question, are we building spurious correlation detectors and calling them explanatory? We need to be careful here about avoiding the illusion of understanding and relying on a model explanation that may not generalize, which was in fact one of Rudin's main points. So speaking of Rudin, Rudin talks about using rules, simplified rules, such as scalable Bayesian rule lists, to try to help understand why a model does what it does. And so here's an example of the output of an SBRL. And these are simpler, but again, I might ask, is this communicating a gist interpretation, or is it simply verbatim rule following? Is it, well, if you do this, and then this, and then this, and then this, you'll get that answer. And I would argue that this does create a simplified representation that helps to understand some structure in the data. But there is still work to be done to try to understand how this relates to the concept of gist that draws on, for example, expertise. And then finally, I want to sort of draw your attention to some interesting developments in topic modeling. So topic modeling is a set of algorithms that are designed to summarize large amounts of data. And actually, one of the main findings in topic models from 2009 comes from this paper, Reading Tea Leaves, that notes that humans actually do not interpret topics in the same way that that algorithms might, which is to say that when algorithms maximize their predictive log likelihood, we actually get results that are less interpretable for humans. And so this leads to some interesting implications for design. I'm going to sort of wrap it up pretty soon here. First of all, there's a distinction that's made in psychology between coherence and correspondence. Coherence means that you follow the rules, and if you follow the rules, you've done your best, you've gotten the right answer. Whereas correspondence means that you have a result that's the right result, regardless of why. So early declarative AI, rule-based AI, very much emphasized coherence, and that gave us models that we now call white box models. These are models that are very easy for us to understand what they're doing. The problem is, of course, that the rules themselves are brittle. They are very much verbatim models. Modern machine learning, on the other hand, is the opposite approach. It's based on these black box models that tend to have high correspondence, which is to say they actually predict well. but we can't really say why. And so this old psychological distinction between two ways of assessing whether a human being is being rational, are they being coherent on one hand or correspondent on the other hand, may have something to say for our development of artificial intelligence. In particular, it suggests that there may be a third way for us to think through what has been called a gray box model, or I would like to say a model that in some way incorporates expertise. So if we were to go see our doctor, if that doctor is an expert, we usually don't just rely on blind trust. If our doctor says you need a surgery, for example, we don't just say, yes, doctor, whatever you say. We say, whoa, hold on a minute. You're going to cut me open. You better tell me why you're doing that. But the doctor will very rarely tell you all of the biological details of what's going on, because the average patient simply does not know how to make sense of those. Oftentimes the doctor won't say exactly what they're going to be doing, if, for example, if they're doing a surgery. And we don't require that. Rather, we have a dialogue with this expert, and we request that the expert tailor their explanations and their interpretations of what they're going to do to the needs of the user until the point where the user is satisfied. And the user then feels like they can trust the process. And so I would put forward the question of whether we can design models that can be queried to return something that the user interprets as a meaningful gist, realizing that people differ from one another in these systematic ways. And so if we were to have the model interact with the human and then try to figure out what are some of these systematic personality differences by asking, some simple psychometric questions, for example, I would ask, can we design models that can then be tailored, whose output can be tailored for human users? And I would argue that this is actually something that systems engineering has been grappling with for a long time when we've been doing requirements analysis. So oftentimes we have a very complex system that has to meet a relatively simple capability. So for example, in a military context, there may be a capability requirement of delivering a certain amount of force in a certain location with a certain amount of notice. It's a very simply stated requirement. But in practice, will that be done by plane? Will that be done by, by missile? How might that be done? And so, again, I'm going to refer back to this concept of the abstraction hierarchy, where, for example, we might have a system that is designed to make a loan recommendation. And so that functional purpose of making a loan recommendation is then implemented as an abstract function, as a credit score determination, which is then implemented using a deep neural net, which is then implemented using a specific set of computers, which is then implemented on specific workstations. And at each point, we going down the hierarchy, we're asking how the implementation happens, and we're asking why to go up the hierarchy. And so requirements analysis, writing requirements, is fundamentally about navigating that hierarchy. So I'm going to leave us with the following conclusions here. I hope I've made the case that explainability and interpretability are distinct requirements for machine learning systems, and that the psychology literature supports that, and that current approaches to explainable machine learning need to be careful not to lead users to impute causation where there's only correlation, because that might create an illusion of understanding. Users, at the same time, differ in systematic ways from one another that may predict preferences for their level of details and explanations and their ability to interpret model output. And then finally, if we explicitly design interpretations into model output, that may be one way to avoid misinterpretation. If we incorporate within the model output generation process ways of trying to understand some of the features of who's using the model. And so with that, I will open up the floor to questions, and thank you very much for your attention.
Thank you so much, David. This was an excellent overview of various concepts, and I'm kind of looking at some of the LinkedIn session comments which are coming in, and also some of the questions I had. Excuse me. So first of all, what's your view on post-hoc explainability versus making sure the systems engineering approach you were kind of presenting? looking at from a requirements design perspective and then kind of going top down.
Right. So, I mean, I think, if we were to talk about post hoc explanations, post hoc explanations are fundamentally about what it is, what did the model do to get me this output? And I think, we have to be a little bit careful when generating these post hoc explanations to have some kind of notion of fidelity to what the model is actually doing. In many cases, when we're using these local feature importance paradigms or proxy models or things like that, we are providing an explanation.
Mm-hmm.
But that explanation may not be an accurate representation of what the model is doing. And so, an example might be if we were to sort of take the ECOA example, right? Let's say for the sake of argument, someone's loan is denied, and we were to tell them, well, the reason why your loan was denied was because you had XYZ credit history, and that's a reason to deny the loan. Whereas in fact, what was actually going on in the model is the reason the loan was denied was in part because of their credit history, and in part because the model was picking up on some demographic feature, right? Mm-hmm. And that was, for whatever reason, not something that found its way into the simplified explanation. Well, what's going on there is you're creating an explanation that doesn't communicate to the user something very important to them. And these sort of post hoc explanations, therefore, have to be a little bit careful. We have to be careful when we use them because, in part, it's important for us to know what might the user want to know about. And that's not something that we might be able to do algorithmically. The other thing, of course, is that simply generating an explanation just to generate an explanation is not our design objective. Our objective depends on who's going to be using the explanation. If our intent is to debug, then we can actually waste a lot of time generating a post hoc explanation that is too simple. All right, because we don't actually get to what we're trying to get at. If our intent is to explain to a user why they got a result that they got and how they might improve their score, for example, giving them a post hoc explanation that doesn't, improve their score enough to change the output. So again, it would change the number, but it wouldn't change the interpretation of the number. It wouldn't move them into a different category. May end up creating a lot of frustration. Because, for example, somebody may do lots and lots and lots of work, to get a credit history, to get, good credit, etc. And then they still wouldn't get the house. And then they say, but the model said this would help. Well, yeah, it did help. You moved from 52% to 52.2%, right? But did it change the outcome? Not necessarily. And so again, we have to be very careful with these post hoc explanations, not to create an illusion of understanding. And I think that's something that we really need to take into account. It's why we need to combine interpretation with explanation. We need to have the explanation, and we need to understand how is that explanation interpreted by the end user.
Absolutely. And you brought in some really good insights. Now, the one note I made was, how people perceive the output of a model, right? So I think that's a very loaded question because, again, there are so many stakeholders in this whole chain, as you're mentioning. If a developer is trying to understand what the model is doing, they may be more interested in debugging the model and understanding the individual variables, but an end user may have a completely different goal, right? So, and that's where context comes in. So how do we kind of fit in context in these applications? When you're from a modeler's perspective, they may not completely envision where the model will potentially be used, especially with things like automatic machine learning models.
Yeah, that is a wonderful question, and I think we can look for analogies to other domains where very complex systems and complex interactions have been used in unpredictable contexts. So, for example, the U.S. Food and Drug Administration routinely regulates drugs and medical devices that are approved for specific uses. So, for example, you might have a particular drug that is approved to treat hypertension, right? And then that drug that's used for hypertension, in the process of its use, maybe some doctors discover that it also treats another condition. And then doctors start prescribing it for what are called off-label uses. And those off-label uses are not, strictly speaking, covered the same way under regulations as are the initial uses. And depending on that off-label use, it may be disallowed. And so one of the things that that we may want to start to think about is whether the ways in which we monitor the use of AI systems may not have some productive analogies to the ways in which we monitor other complex systems, such as medical devices, right? So with medical devices, we do randomized control trials to make sure that they are safe and efficacious before they are deployed. And then once they are deployed, there actually is an extensive post-market surveillance infrastructure that is deployed to make sure that the device isn't causing harms that weren't captured in the randomized control trials. And that includes, in many cases, off-label uses. And simply having the data of how, I'm not claiming that that system is perfect, by the way, but simply having the data creates a lot of insight into the ways that these things may end up being used. And, you know, it's certainly not my position to make any statements about what our regulations should be, but I do think that there are some interesting prior examples of our ability to roll out complex systems. If we look at the FAA and the way that the FAA treats safety critical systems as well, we'll see that there are specific considerations and uses for airplanes and for airplane parts that are simply allowed because they've been tested, which is not to say that they couldn't be used for other things. I can imagine all sorts of uses for a jet engine, but those are not legal uses.
Right.
Because if we use them outside of those contexts, somebody might get hurt. And so I think, you know, there are several sort of adequate examples from other fields, and the question becomes, you know, which one do we choose and which one do we go with? And I think that that's in part my hope that we would have a robust dialogue around that.
Absolutely. I really like the systems engineering approach. You know, me being a mechanical engineer by undergrad training myself, I really love the engineering way of thinking. And when we build solutions, as an AI designer, when you're kind of, you know, designing these systems, many times we are just focused on, you know, optimizing certain outcomes, and explainability may not be something on the top of our list onto, you know, things to optimize, right? And that's where, when you deploy some of these systems, you may be wondering like, okay, well, this is the explanation, but you kind of, you know, touched upon things about like, well, different users may need different levels of explanation, even with the diagnosis example you were kind of, you know, giving. You know, doctors may be saying, okay, you know what, we will do this procedure for you because this is good for you, and it's going to increase the knee, or, you know, the whatever you know, solution the doctor is prescribing. But then based on the dialogue, it could be that the person may be educated or may be open to receiving more information to make the decision, right? So there could be, you know, doing more research and saying, hey, I found this other alternative approach or this particular thing. So why shouldn't I be doing this? Why shouldn't I be extending my, you know, working in this particular way? So how do we enable those kinds of aspects in either design when you're kind of, you know, building these kinds of solutions, or even formalizing it so that you can provide that level of details when it's sought out, rather than just saying, well, this is like the 2-line explanation we give you at this point, and sorry, we have denied your loan and we cannot give you more. This is the only thing we can tell you at this point.
Yeah, so I think that's a wonderful question. I mean, look, ultimately we have to recognize that these tools are embedded within a use context, and that use context is going to drive how they're used. You know, nobody would ever go to a medical device manufacturer, somebody, for example, who makes pacemakers, and say that the pacemaker must provide informed consent to the patient. Right? It's not the pacemaker that does that. It's the pace. There's documentation with the pacemaker, and then there's the doctor and the treatment team, and then, you know, they go through the information together as a team, and they figure out, you know, is this something that the patient truly wants to do? You know, there's a profession in public health, health communication. There are professional public health communicators. In artificial intelligence, we're very much coming from a culture where we try to automate as much as possible and remove the human from the loop, because that's really what's led to these massive kinds of, progress in what AI has done. But I wonder whether it might not be prudent to start thinking about, what sort of training people might require to become algorithmic communicators. If we wanted to say, for the sake of argument, that we would train people to help others understand what it is algorithms are doing in what context, what would that training look like? And would that be something that could interact with an automated system, or could in some way build on an automated system? Certainly, we should do our best to make the system itself as transparent as is necessary. But of course, we know from our own design experiences that transparency is not, as you stated, sometimes that transparency comes at a cost in performance. And so then the question is whether it's worthwhile to train people to basically develop that deep understanding of what that model is doing, and then help explain it to those who don't have the time or the inclination to dig into the guts of the algorithm itself.
Absolutely.
So I mean, I think that's one possible approach. Certainly, there's a whole other discussion to be had around whether some models are even, explainable at all, given how complex they may be, and that's certainly a wide open area of research, not just in AI, but in all systems engineering.
Yeah. And that's a great point, especially with the communication aspect of it. I mean, as an educator myself, sometimes I struggle on how much should we be teaching our students, especially with the metrics and the processes. But you can't just give them all the context, because you will be applying those tools and methodologies in specific contexts, and then you'll have to start understanding the context better so that you can design these systems well. But with the proliferation of all these automatic machine learning tools and heavy emphasis on tooling, I think the communication piece is one thing I'm seeing is heavily lacking. And the whole reason why everybody is saying, well, you need to be making so much efforts in increasing transparency, because someone else should be able to take a look at it and agree to what you're saying, or someone else should be able to explain it for you, especially if you're not able to hire the PhDs within your organization to even build out the technologies. As many companies are building out no-code, low-code solutions, primarily saying that we don't have the skills in the industry to basically go in and kind of look at it at a very granular level on what's actually happening under the hood. So how much do you think should the tools be looking at providing these kinds of explanations versus having a whole profession of algorithmic auditors who are meant to be the explainers, meant to be the communicators, and meant to be the people who you would trust, and kind of by association you would trust the tooling or the product because you trust a particular organization, or you trust a particular reviewer who has in a neutral way looked at the solution and provided insights regarding the explanations of what the model is doing.
Right. I think that's a wonderful question, and in large part that'll depend on the state of the technology at the time. Certainly, algorithmic approaches to providing interpretations and explanations may make significant advances. And I think if we can look at the topic modeling literature, there have been several wonderful advances in measuring the interpretability of topic models. But there are also, of course, for each of those advances, there are other findings pointing to the need to do more. And one of the things that will likely come about as people start to approach this problem is, well, they'll quickly realize what are some of the limitations of algorithmic approaches. And I think we still need to do a lot more research to understand from a design perspective, what can we put into the output of a model that can help people to derive the right gist.
Right.
And to be blunt about it, what are the conditions under which people can draw the wrong conclusions? There's a whole literature in psychology going back to the 1970s called the heuristics and biases paradigm that shows that people are subject to systematic distortions when making decisions based on probability. And so the question is that something that we can help people to overcome on one hand, or on the other hand, is that something that by relying on the model to communicate, we might actually be making worse, and therefore we need to have a human in the loop somewhere, right? And so, these I think are very much open research questions, and I think it's very exciting to think through where the field might go in the future.
Absolutely. This was a fascinating session, David, and thank you so much for spending time with us and clarifying so many of these concepts. And I'm going to go and digest the slides and also the paper in a new light now that we've had this opportunity to kind of, listen on what your thoughts are regarding this topic. And as most of you know, David has written this paper and a couple of other works. We were kind of discussing about the 4 principles paper on which you were co-authored. So I think David has contributed a lot to the literature. So I would highly advocate you to go to the NIST website and check out some of the other publications. Thank you again, David, for making time for us today, this afternoon. And for people who are listening in, next week, we're going to have another session, and we'll also talk about the upcoming spring school offerings. So please make time to join us again next Tuesday at 12 o'clock for the QuantUniversity Fall School. See you again and have a wonderful rest of the week. Thank you.
Thank you very much.